Hello and welcome YouTube, Mr. Robinson back here with yet another brand new and exciting video. TV on and all math based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and apologies for my disheveled appearance. If you guys don't know, whenever you're like, oh, why is he always wearing the same thing? I coach softball and I come from softball practice, but I noticed I have a lot of hat hair today. Got a little sweaty out there. So sorry for the appearance. You don't have to look at me very much or the CV very much. It's more so for me and my reactions to certain things. I feel like I got to sneeze, so I might have to in a bit. I should probably pause for that. But we're in section 3.6 of the Big Ideas Math Integrated Math 2 textbook on focus of a parabola. Also, another word called directrix should be involved here. This is generally something that you don't see until IM3. I'm actually kind of surprised that it's here. It's nice. It's fine to have it. And I only hope I can do the book service when it comes to the problems, because if they overspeak on something or underspeak on something, I might go the other way. If they represent a formula kind of a little bit differently, you might see how I go about doing that. But hopefully I can, again, give it enough service, or at least give you enough service to understand the material. That's the point. As we go through the problems, I forget how many are in the problem set. It might be up to 50 something, 40 or 50 something, and we'll see how long it goes. So I'm glad to get this one out of the way. Let's go ahead and take a look at the lecture portion, and then we'll go to the problem set. Check the description section down below if you want to find certain timestamps, certain things, and the PDF of this section itself. 3.6, focus of a parabola. Your core vocabulary are the words focus and directrix. Okay, we will explore the focus and the directrix of a parabola, new terms for you guys, and a new way of looking at the parabola. There is plotting points, but there's also getting these two identifiers within it. We're going to write equations of parabolas, kind of the same as before, only we're going to do it off the focus and the directrix likely, I'm guessing, and I'm still going to make sure to graph parabolas along the way if we do that, and solve real life problems. Give me one sec, as I was about to sneeze. I think I'm about to here. Okay, it didn't yet, but I didn't want to let it interfere. Okay, exploring the focus and directrix. So previously, we know that a parabola could open up or down. That's what this says. But a parabola isn't just about the whole x squared thing. 1, 1, 2, 4, 3, 9 times the stretch factor and things like that. That's a part of it. But the points themselves, all of those points on the parabola are some distance away from something. Here's what it's going to say. A parabola can be defined as the set of all the points in a plane that are equidistant from a fixed point called the focus and a fixed line called the directrix. And they're going to show you it right here. Here's your parabola. Let's say it's this blue guy right there, okay? Here's the x-axis, here's the y-axis. No, excuse me, that's not the x-axis. Here's the parabola, and here's the axis of symmetry. Now, there's this point right here. This point is known as the focus. It is always inside of your parabola, and that's important to note. Wherever your focus is, it's inside the parabola. The distance from some xy, here's some point on the graph. Here's some point on the graph. Here's some point on the graph. The distance from the focus to that point, or that point to the focus, is the same as the distance to this other line known as the directrix. The directrix is this line, always outside of the parabola. And these two distances are congruent to each other. You can see that right here. This distance and this distance are the same. This distance and this distance are the same. And this distance here and this distance are the same. And these two distances are going to be very specific values we're going to use. I got to see which letter they use, probably P. But these two distances are very specific. The one from focus to the vertex and vertex to directrix. Okay? But these are all congruent in that way. So how do you make a point, or how do you make the distance from a point to a line? You got to go perpendicular to that line. So this has to go perpendicular to it and perpendicular to it. It's the shortest distance to it. And those distances are all symmetrical. So, those distances are equidistant. So this and this are the same. This and this are the same. And that's true for all parabolas. It's really cool. Okay. Now, that might be a little lot for you to start off with, but we are going to deal with it. That's what that is. And yeah, the focus is in the interior of the parabola. The directrix is outside the parabola. It's perpendicular to the axis of symmetry. That's a good way of putting it. Perpendicular to the axis of symmetry. And the vertex is half the distance between the focus and the directrix, at least the closest points. And like I said, we're going to be working off a specific letter. I think they're going to be using the letter P to denote this distance here in just a moment. But those are the same distance away no matter what your XY value is. So we're going to do examples, I suppose, where you use the distance formula to write an equation. Now, the distance formula, let's see if they say that anymore. I see instances of it. So kind of like this right here. The distance formula is the square root of your 2x value subtracted squared plus 2y value subtracted squared. It's a way of, it's a bit like Pythagorean theorem. And this, I'm just going to assume that you know how to use that, because it looks like we're going to be using it here. Notice the line segments drawn from point F to point P and from point B to point D. So here's your focus. Here's a parabola. I guess this is the x and y axis. Here's your focus at 0, 2. Here's your directrix. The equation of the line is y equals -2. Now there's some xy point that's on this parabola here, and the directrix point, the one we draw to, is the same x distance away right there. The y value is -2, this y value is unknown, and this parabola, or excuse me, the focus, like I said, is at 0, 2. We want to find the distance of this segment and the distance of this segment. They're going to use distance formula for that. Now, I can't imagine that I need to actually use distance formula for this one, but it looks like they're going to. I might find a shorter way of referring to that in the future, but we can still go ahead and do that. So what we're going to do is say that, hey, PD, this distance here, this distance of segment PD is equal to the distance of segment PF, right? Those are both congruent. Now, we can use the distance formula to say the distance from this x to this x, PD, x minus x sub 1 squared, plus y minus y sub 1 squared. So my x minus x here, x minus x squared plus y minus -2 squared. That's using distance formula from this point to this point, those x's and those y's. And it equals, so from this x to this x, we're going to do x minus 0 squared plus y minus 2 squared. So we're substituting here. X minus x is 0, 0 squared is 0, plus y plus 2 quantity squared, and you're taking the square root of that. And then here we have the square root of x squared, because that's x minus 0, and y minus 2 quantity squared here. Now, they ended up squaring both sides, and the reason for that is because you can't simplify this inside. The square root of y plus 2 squared may be y plus 2. However, the square root of x squared plus y minus 2 squared is not x plus y minus 2. It doesn't work that way when there's a sum right there. So if we square both sides, then we get rid of the square root guy right there. So squaring this gets rid of that square root, and squaring this gets rid of that square root. And now we can deal with just x's and y's together. We're not going to solve for something except for getting one of the variables by itself in terms of the other variable. So we expand this to y squared plus 4y plus 4. We expand this guy to y squared minus 4y plus 4. And the y squareds cancel out here. I can add 4y to this side. I get 8y. I can, the 4's cancel out. And I get 8y equals x squared. Divide both sides by 8 or multiply by 1/8. You get y equals 1/8 x squared. Now, you're going to be seeing a lot of different equations in this form. And like I said, it's probably going to show up a little bit later. Or we have to go slowly through this each time. I don't know if this is going to be a very long video or a very short video or what. But there is using the distance formula to come up with an equation based off that focus in that parabola. There's a formula involved. Maybe we get to play with it later. But for now, we might have to use distance formula to prove it. They show us the relationship here later, so maybe we don't have to do it later. So there's a proof with this given any 0 comma p right here, meaning this distance right here is p, and then this distance here is technically also p. So p units up and p units down from the vertex. We can get our focus and the closest point to our directrix from the vertex right there. So kind of a negative p, if you will. Then we're at 0p here, and this is at x comma -p here. You can use distance formula once again to set both sides equal to each other because they are equal segment lengths here and here. And then if you clean all this stuff up, I'm not going to run through the entirety of the proof unless I have to later. But if you clean stuff up the same way you did before, you get this relationship in this equation for this parabola, y equals 1/4p x squared. Now, if you saw in the last problem, well, it looks like they'll talk about it more here. Actually, they'll talk about it right here. Perfect. But the focus and the directrix are both p units away from the vertex. We're going to use that letter p very specifically. Last time the number was 2. And then we can write equations in that form. So let's look at this core concept. This is going to be a huge thing to look at right here. When you have an upward-facing parabola, you have a y equals x squared equation, of course, but p is a positive number in this case, and it's going to be a 1/4p x squared. Now, if you notice here, it says, notice that y equals 1/4p x squared is of the form y equals ax squared. So when you have y equals ax squared and y equals 1/4p x squared, it looks like the relationship here between a and 4p is that a equals 1/4p. And that's something that I'm going to happily use in the future, meaning I'm probably not going to write things like this, but I'm going to keep this one thing in mind. Now, once again, a is your vertical stretch factor, but p is the distance from your focus to your directrix. So depending on the information that we have or that we need, we're going to go ahead and do that. This is where I said I might not be using the books as much service because I don't know how they're going to write it, but here's one way. If you solve for P and get A on the other side, you'll get P equals 1 over 4A. And notice these are denominator values. These both work opposite ways. So if I knew the stretch factor, I could find the distance from focus to directrix and focus to vertex. If I knew the focus to distance from focus to directrix, focus to vertex, etc., I could find my stretch factor. If we have to use some of that Pythagorean theorem, distance formula to work out some of those to begin with, fine. Eventually, if we don't have to do that, I'm jumping straight into this. Anyway, so notice focus is inside the parabola if it's upward facing. Directrix is on the outside and it's a horizontal line. If your graph faces downward like this, P is a negative number, then it's going to be 1 over 4P. Therefore, if P is negative, A is also negative, right? And it goes upside down like that. You can have sideways parabolas. They're not functions, but you can make sideways parabolas in an x equals y squared format. X equals y squared. Of course, you'll see me have x equals a y squared. Horizontal stretch factor now will be the a value. But as a parabola goes sideways, x equals y squared, just like this, you can see the focus inside the parabola. Once again, directrix on the outside. It's now an x equals equation because it's a vertical line. And same with if it faces to the left. That's if P is negative, and if A is negative going to the left. We're just going to have to get used to that idea. We can go up, down, left, or right. These are non-functions. These are functions, but we can still make equations based off that. That distance P stays consistent on these things. Now, the bigger that P is, we didn't get to play with this, but the bigger that P is as a number, the wider your parabola goes. You're going to get more of those fraction values. The smaller that P gets, the taller and more shrunk this gets. So I don't know what the examples will look like. Okay, identify the focus, directrix, and axis of symmetry of negative 4x equals y squared in this equation. Graph the equation. They say rewrite the equation in standard form. Now, if you notice, x is the one that is not squared, y is the one that is squared. So you want to get x by itself, make it say x equals negative 1/4 y squared. In this case, x equals negative 1/4 y squared, your a value is negative 1/4. Now, what I'm going to do, I don't know if they're going to do it the same way here. If a is negative 1/4, then negative 1/4 equals 1 over 4p, right? A is 1 over 4p. Or you can say p is 1 over 4a, like that. I'll probably do more of this one. 4 times negative 1/4 is negative 1, and that's your p value, and that's what they say right here. So a is 1 over 4p, p is 1 over 4a. You can use that instance to go ahead and find the other value, because they're going to ask us to identify the focus and directrix, and we need p for that. They also say graph the equation, which we'll talk about. Axis of symmetry is something. We can do the axis of symmetry and graph first if we needed to because we have the information, but we can also get the p and stuff there. Now, if p is negative 1, and honestly, I'm not saying it doesn't matter what the sign is, but because I know that a is negative and it's an x equals y squared equation, I know it will graph left. So even if I said p was positive 1, I still know I'm going to go 1 unit inside of here to get the focus and 1 unit outside of there to get to the directrix. So when you find your vertex, which is at 0, 0, it's at the origin, just an x equals y squared equation, all normal, and that's probably what they're going to do for us all the time, 0, 0 focus. We can do a, if it's a sideways parabola, we have that concept now of 1, 1, 2, 4, 3, 9, 4, 16, like I've done on previous graphs. Only now, and they used a table, only now we take a quarter of these values. It's a horizontal compression. 1, 1/4, 2 1/4 of 4, 3 1/4 of 9, 4 1/4 of 16, like that. And then you can plot your focus 1 unit away from your vertex and your directrix line 1 unit away from your vertex as well. Why 1 unit away? Because p is negative 1. If this is confusing, it's your first time seeing it, I totally understand. This is something, like I said, that covers more in IM3 for the most part, but that doesn't mean you can't understand it here as well. It's just something we have to pick up on more. Okay, let's write the equation of a parabola. Now, if you're given a graph, I suppose, if you're given a graph, if you're given information on this thing, how do we write an equation off of it? So here we have this vertex. We can see it's a y equals x squared equation. It's an upside down one. We expect some y equals ax squared form. We basically have to find a, and it's based off of p. In this particular problem, you're given the directrix right here. It's 3 away from the vertex. That means you have a p value of 3. In this case, it's probably a negative 3. Again, if you didn't know that it was negative, it's also because the graph goes upside down. The focus would also be 3 units away right here. Doesn't really look like we need the focus, though. In this case, the focus would be right there, though. But we just need to know what p is, right? If a is 1 over 4p, then a is 1 over 4 times negative 3 in this case, which is negative 1/12th. And that's the a value that they also get right here. 1 over 4p is negative 1/12th. So your equation is y equals negative 1/12th x squared. And I know it's a y equals x squared equation because it's an up or down facing one. I know it's negative because it's down facing. We can do some more when we hit some of the other problems. Okay, looks like we're not always on the vertex, so we have to keep going here. So if you notice, and listen, they're getting pretty heavily as far as this formula stuff. I'm not getting big on that. What I'm going to do is give you your y equals a times x minus h quantity squared plus k vertex form of this guy. I'm going to plot the vertex, and I get to go p units up or down from there once I have that vertex graphed. So not going to get too big on, remember the focus is at k times, or h plus, etc. It's p units up from here, p units down from there once we get that vertex plotted. So I'm going to get a little more on that so we're not trying to over memorize something. Now the one thing here you got to be careful of in an x equals equation is now y is the one that has k married with it right here. Y minus k quantity squared plus h. Your vertex is still at hk, but now h is on the outside, and h doesn't have its sign changed. Now k has its sign changed because it's with y. So there's a reason why we change a sign. It's not always k, just depends on your equation. Now the a value, again, is a horizontal stretch factor. It's still 1 over 4p, and I still go p units away this way and this way, inside and outside the parabola to get those things. So we're going to be able to write equations based off that more and more, and it looks like we're going to do some off of the origin. I didn't know that we would. So let's write an equation of the parabola shown right here. We have a vertex of, look how these are scaled by 2's. This is at 6, 2. That means that's your h and k. H is 6, k is 2. Notice it's going to be an x equals y squared equation because it goes in this direction here. So they're going to be using that. H is 6, k is 2, y minus 2 quantity squared plus 6. So they probably have that written somewhere. Not quite. And then this p value, the distance from vertex to focus is 2. That's your p value. So a is 1 over 4. Normally I'd have them write it, but I'll show you how I'm going to write it. 1 over 4p, which is 1/8. So your equation is going to be x equals 1/8 times y minus 2 quantity squared. Excuse me, what did I do here? Oh, this scales by 2's. I forgot. That's 4. So 1 over 4 times 4 is 1/16. And this is 1 over 16. 1 over 16. Those are scaled by 2's. So 1 over 16, as you can see right there, and you get the same equation. Like I said, I'm going to go pretty fast on those ones when we hit them. Or, excuse me, I'll slow down more. I'm going fast now because they all have that written. Real life problems. Parabolic reflectors have cross sections that are parabolas. Okay, we've seen that before. Incoming sound, light, or other energy that arrives at a parabolic reflector panel, the axis of symmetry is directed to the focus. So you can see that you go from the focus, it goes in there, boom, and it bounces off in such a way. Similarly, energy that's emitted from the focus of the parabolic reflector then strikes the reflector is directed parallel to the axis of symmetry. So they, boom, reflect and go that way. Okay, that's fantastic. Let's see what we do off that. An electricity generating dish uses a parabolic reflector to concentrate sunlight onto a high frequency engine located at the focus of the reflector. So we got an engine right here. We are going to generate energy where the sun rays come into here and go right into that focus, right? That's where they bounce off. They don't just go this way, they also go that way. Cool. The sunlight heats helium to 650 degrees Celsius to power the engine. I don't know if that's required for us to know. Write an equation that represents the cross-section of the dish shown with its vertex at 0, 0. So we see that this value here, 4.5, represents the p value, distance from vertex to focus. That's going to be p of 4.5. 8.5 is the width of this thing. That doesn't really matter until we do something with that. I'm going to see what we're going to do with that. Write an equation. What is the depth of the dish? Oh, okay. That'll be used, I guess, once we get our equation. Maybe we get to plug something in to get that depth. And I see what we're going to do there eventually. So we're going to use this p to get this stuff. We already know the vertex is at the origin. It's a y equals x squared equation. In this case, ax squared, because it's at the origin. A is 1 over 4p. So 1 over 4 times 4.5. They use that right here. It's 1/18. So your equation is y equals 1/18 x squared, like that. Boom. Now, in order to find the depth of the dish, we got to find out how deep it is, from here to here, just alone. Don't assume it's half of p. What we got to do is find out what this point is on the graph. Remember, they're talking about this being our parabola in a cross section. If this distance is 8.5 across from here to here, that means half that distance is 4.25. This is where x is 4.25, comma 0, I should say. So this is 4.25, comma some y. So we substitute 4.25 into our equation for x. It looks like it approximates to about 1. So the y value is 1. That means that this distance here is about 1. That is the depth of the dish, about 1 meter. So there's a real life problem that seems fun to do, and it looks like we're going to probably do some of those in just a moment. Yay, we're getting into some of the problems here. So pardon the 20 minutes of work on the lecture. Let's see how long this will end up taking. It might be a little while. Let's start with the completing the sentence. A parabola is a set of all points in a plane equidistant from a fixed point. That fixed point, guys, is known as the focus, and the fixed line is known as the directrix. Directrix. Explain how to find the coordinates of the focus of the parabola with the vertex at 0, 0, and directrix at y equals 5. I'll explain through a drawing, and then I'll type some things out as needed. So here is your vertex at the origin. The line y equals 5, and I'm going to draw as a dotted line when I do it. I'm going to use the line tool, but it's going to be a dotted line for the directrix. It's a horizontal line. That means this graph goes upside down right here because your focus, the vertex is right here. The parabola goes upside down because the focus is inside of it on the other side opposite. The directrix is p units away from the vertex, and the focus is also p units away from there in the y direction. So if the vertex is at 0, 0, and this thing is p units up from here, then this would be p units down from there, right? You subtract p to get that. So the coordinates are going to be 0, comma, negative p in this case. And, your p is 5. I didn't even notice that. Y equals 5. So it's going to be at 0, comma, negative 5 right here. If this is 5 units up, this is 5 units down. So the reasoning, again, for all this is that the y equals equation being up above means we know we go downward. It's a y equals x squared equation. The focus is underneath that, so we're going to go down p units from there, the same p units as we are from the directrix. If the directrix is 5 units away, so is the focus. And 5 units from the origin, downward, is at 0, negative 5, right there. Okay, I'm going to go ahead and move forward to the actual problems themselves. We were probably going to do some of the distance formula once to start. If so, that's going to take some time. Hopefully, once we get to the 1/4p stuff, I'll go a little bit faster, but, we do what we do. I probably am just going to attach the squared graph paper because we're going to do as many x equals y squareds as y equals x squareds. So we'll see where we actually end up going from that when we try them out. I haven't done the problems before. Yet, so I don't actually know what it's going to look like when we do it all. But let's go ahead and get started right now. Let's use numbers 3 through 10 to use the distance formula to write an equation of the parabola. So like I said, these problems, I'm going to find other ways to speed them up meanwhile. We do know there's a 1/4p relationship, but at this point you didn't yet know this, and that's why we're going to practice the problems just like this. So what I'm going to do is I want to find the distance from here to here, the focus to the point on the graph, right? So we know that the segment length FP is going to be equal to the segment length PD. PD, that's the distance from this point to the directrix itself. So these are the same length. So we want to use this distance formula to show that those two things are equal to each other and then get the equation. Now, I'm projecting my equation is going to be y equals 1/4 x squared. I'll write that each time. That's because we know that the p-value looks to be 1. But we don't know that yet. So let's go ahead and jump into it. So distance formula is the square root of an x, in this case the actual unknown x, like this unknown x. This is for FP, by the way. This is going to be x minus 0 quantity squared, this other x I'm talking about right there. And then I'll do plus y minus 1 quantity squared. Plus y minus 1 quantity squared. And this equals, let's move that. And then on this side, we're going to have an x minus x quantity squared plus y minus negative 1 quantity squared. Now, x minus x is just 0. Nothing's going to change on that. But, so after this problem, I'm probably not going to do it that way. If you have vertical or horizontal distances, we can equate that different ways. But x minus x quantity squared plus y minus negative 1 quantity squared. That's your distance formula for both of those. X minus 0 is x, so we get x squared, plus y minus 1 squared is y squared minus 2y plus 1. And yes, I'm expanding early. Sorry about that. It's just I'm doing what I can early. X minus x squared is 0, so that's 0 squared is 0, plus y plus 1 quantity squared. Y plus 1 quantity squared. We're going to square both sides of this equation. We're going to start to get one of the variables by themselves. And in this case, we have x squared plus y squared minus 2y plus 1. Again, I did that prematurely on the expansion. And y plus 1 quantity squared is y squared plus 2y plus 1. Subtract y squared from both sides, those cancel. Subtract 1 from both sides, those cancel. And you're left with x squared minus 2y equals 2y. So x squared minus 2y equals 2y. If I add 2y to both sides, I get x squared equals 4y, or 4y equals x squared. And if I divide both sides by 4, I get y equals 1/4 x squared, which seems to be the answer that I expected all along right there. So y equals 1/4 x squared. And that is number 3. So you can see where these problems could take some time. I'm going to do some things to streamline this, and I'll show you how that's going to work next. Number 4. First of all, an answer that I expect. This p-value is -4. We're going downward. It's a y equals x squared equation. This is the vertex at the origin. I expect this answer to be y equals 1/4p x squared, or -1/16 x squared. So it's an answer we expect to get later. Again, I want to utilize this because we're going to be doing this a whole lot more later than not 1/4p, right? A is 1/4p. Okay, so once again, FP equals PD. We're going to set those two segments equal to each other. The distance from 0 to x is just x. So again, I'm going to speed some stuff up where I can. So the square root of x squared, that's your kind of a squared here, and plus b squared is the distance from y to -4. So that's y minus -4, or y plus 4 quantity squared. Now this distance right here from, it's a vertical distance. This length is y, this length is 4. We need to find the distance from with y and 4 there, and that's going to be y minus 4. Notice how the x's are not involved. The x's would just cancel when you subtract. I am using distance formula. There's nothing I'm not doing there. The distance, and honestly, I don't even need to put this part where I need to put the squared part. I'm going to evade that next time as well. The distance is y minus 4. So if I square both sides right now and also expand along the way, I'm going to have x squared plus, the square roots cancel, y squared plus 8y plus 16 equals, and this is y squared minus 8y plus 16. Y squareds cancel, 16s cancel. I can subtract 8y to both sides here, and I'll get x squared equals -16y. If I divide both sides by -16, I get y equals -1/16 x squared, which is what we got here, over there. So you can see there's a lot less work that I need with that. I'm still using distance formula, or I'm using distances to get them, not just 1/4p. Number 5, the focus is at 0, -2. The directrix is at y equals 2. It helps to draw out this graph. It's going to be a very quick one because you do need to know which direction these things go as well. Focus is here at 0, -2. That's your focus. Directrix is y equals 2 right there. It looks like the vertex is still right in the middle, V, and this graph will go upside down, which is a nice way to look at that. This distance here of P is once again -2. P is -2. So when it comes to the actual equation, A is 1/4 times -2, or -1/8. It is a y equals x squared equation, so this will be y equals -1/8 x squared. Let's go ahead and get that answer using distance formula. Let's plot a point on the graph that is some x comma y, right? That's what we're doing. Given some x comma y, I need to find this distance and set it equal to that distance. So here's that focus point. Here's the directrix point. This directrix point is 2 up. This is at x comma 2. Whoops. Directrix is at x comma 2. So the same stuff before. This distance is just y minus 2. Y minus 2. Because it's the distances between that y and that thing here. And this distance here is the square root of x minus 0. That's x squared plus y minus -2. Y plus 2 squared. Now if I square both sides, I get rid of this radical right here, and that will square this part naturally, just like we would have with Pythagorean theorem in the square root canceling. We're going to have x squared plus y squared plus 4y plus 4 expanded equals y squared minus 4y plus 4. Y squareds are going to cancel once again. 4s are going to cancel here. I get to subtract 4y from both sides, and I'll get x squared equals negative 8y. Divide both sides by negative 8, and you get y equals negative 1/8 x squared. Once again, what was expected over here. Number 6, we'll have a directrix of y equals 7 and a focus of 0, negative 7. Very much like this problem was before presented, only now it's a little bit farther off. The vertex is still here. Directrix now at y equals 7, focus at 0, negative 7, and again the vertex is right in the middle of those at 0, 0, just like that. We're going to have some point on the graph that's going to go perpendicular to there, and we need to see that those distances are the same. The point is at some x, y. This point is at x comma 7. So the distance between x7 to xy is y minus 7. So this is going to be y minus 7 equals, that distance equals, Pythagorean theorem, x squared plus y plus 7 squared, or y minus negative 7 squared, and take the square root of that side. We are going to square both sides, and when we square both sides, we'll get x squared plus, and expand that, y squared plus 14y plus 49 equals, and this is, when you square this side, you get y squared minus 14y plus 49. Once again, you can see little corners that I'm cutting with that. It's not out of measure of like, we're still doing all the distance formula stuff. We're just kind of showing the distances in other ways that can clean up our actual work. Subtract 14y over, I'm going to get x squared equals negative 28y. Divide both sides by negative 28, you get y equals negative 1/28 x squared. And I forgot to predict what this answer would have been, because this distance here from vertex to that p-value is negative 7. Your a is 1 over 4 p, which is negative 1/28. So we would have had that equation. We would have had that equation there anyway. Okay, number 7, we have a vertex at 0, 0 and a directrix at y equals negative 6. Let's see where this graph would have looked appearing wise. Vertex is at the origin. Y equals negative 6 is down here, so your focus is going to be up there. Here's your vertex, there's your focus. We're going to pick a point on the graph, some x, y. Now, this is not drawn to scale, but what we're saying is this distance is the same as that distance right there. Clearly not the same. However, what we do know is that if this is 6 down, then this is 6 up. Your p is 6, so your a, 1 over 4p, is 1 over 24. It is a y equals x squared equation, and it's a positive one. So we're going to have y equals 1/24 x squared. Let's use distance formula to confirm that. This was at x negative 6, and this guy is at 0, 6, because we're going to be p units up here. So the distance from f to p is x minus 0 quantity squared plus y minus 6 quantity squared equals, now here the distance from y to negative 6 is y minus negative 6 or y plus 6. We're going to square both sides here and expand the y minus 6 here and expand that. We'll get x squared plus y squared minus 12y plus 36 equals, expand that, we get y squared plus 12y plus 36. Once again, the cancellation of our y squareds and our 36s, like that. I can add 12y to both sides here, and I'll get x squared equals 24y. Divide both sides by 24, you get y equals 1/24 x squared. Looks like all of these are going to be y equals x squared equations to start with. Not until we hit later example problems did we hit x equals y squareds, sideways parabolas, but we are going to hit some of those eventually, I am sure. Number 8, our vertex is at 0, 0, and our focus is at 0, 5. I hope after these first ones, honestly, we get to use the 1 over 4p and not distance formula to necessarily have to do them all. You know what I mean? So your vertex is at the origin. Boom. Your focus is up here at 0, 5. We have a parabola that's, I'll widen it out a little bit more. Your directrix would have gone all the way down here at y equals negative 5. So when you have a point on the graph at some x, y, the directrix point that we get to go to for these segments to be equal, and that looks a lot more drawn to scale, is at x negative 5. 5 units up, 5 units down at y equals negative 5. So the distance from f to p is, oh, by the way, 1 over 4p. A is 1 over 4p. 1 over 4 times 5 is 1/20. I expect y equals 1/20 x squared. Let's see if we get that. So the distance from f to p is x minus 0 squared plus y minus 5 quantity squared. The distance from p to d, this point here, is y minus negative 5 or y plus 5. Let's square both sides. And we are going to get x squared plus y squared minus 10y plus 25 equals, and here we get y squared plus 10y plus 25. Y squareds and 25s cancel. As you subtract them from both sides, I can add 10y to both sides. You get x squared equals 20y. Divide both sides by 20, you get y equals 1/20th x squared. I believe that's what I said, because the 1 over 4 times 5 would have given us 1/20th. And, no, not lastly. Two more. Number 9. The vertex is at 0, 0. The focus, and sorry I haven't been copying down those specific things. I've been writing it on the problem itself. It's just it doesn't develop all the information that we get, though. But the vertex is at the origin. The focus here is at 0, -10. Our graph is going to go downward into that focus. The directrix will be 10 units up from there at y equals 10. When you hit a point on the graph that's some x, y, then the point to the directrix goes straight up to there at some x, comma, 10 units up. And this distance here is going to be that. These distances are the same, so let's set them equal to each other. The distance from here to here is y minus 10. You can write 10 minus y, by the way, if you weren't certain which way to put it. You can write that. It's just when I square it, you're going to get the same result, and I like my variable first. From f to p, x minus 0 is x. We square that. Y minus -10 is y plus 10. We square that, and we add the results of both of those. Let's square both sides here, and we're going to get x squared plus y squared plus 20y plus 100 equals, and we square this side, we get y squared minus 20y. Let me move that over just a little bit. Y squared minus 20y plus 100. Subtract y squared from both sides, subtract 100 from both sides, and we can subtract 20 from both sides. We get x squared equals -40y. Divide both sides by -40, you get y equals -1/40th x squared. I hope I don't have to graph something, so divide them by 40. That's going to be quite a bit when it's going to be very wide. And that's what I'm saying. The farther apart the focus and directrix are, the wider the parabola has to be to make those points equal the way that they are. The focus and directrix actually really do matter when it comes to them. It's actually super cool to see that relationship happen. Okay, and again, the p was -10. 1 over 4p is 1 over 4 times -10. That is -1/40th. That's where it comes from. Lastly, number 10, when it comes to this set, we have the vertex at 0, 0, and the directrix at y equals -9. So the directrix is down here at this guy. I think if anything, you're also just practicing the location of these values. So your p-value is going to be 9, because we're going to go 9 units up to here as well to the focus at 0, 9. This graph will go upward into that focus like so. And we pick a point on the graph, some x, y, so that these two distances are the same. At the directrix, this is x, comma, -9. That's y equals -9. So we find the distance between all those. 1 over 4 times 9 is 1 over 36. So I'm expecting y equals 1/36 x squared. So we're going to say the square root of x minus 0 squared, or x squared, plus y minus 9 squared equals this vertical distance from x to x is 0. From y to -9 is y plus 9. And we square both sides here. And we're going to get x squared plus, expand this, y squared minus 18y plus 81. And this equals y squared plus 18y plus 81 right there. Subtract the y squareds from both sides, they cancel. Subtract the 81s from both sides, they cancel. Add 18y to both sides, and you'll get x squared equals 36y. Divide both sides by 36, you'll get y equals 1/36 x squared. I do believe that that's what I said is my value. And that is number 10. Okay, the first ones went very slowly because of the distance formula stuff. Other problems can go slowly because of graphs, but let's see what happens next. Number 11, analyzing relationships. Which of the given characteristics describes parabolas that open down? Explain your reasoning. So, let's see what I need to write here. It says which of the given. I don't know if it's more than one answer. When you see a focus of 0, -6 and directrix of y equals 6, this one will indeed open downward. A is going to be one of them because the parabola goes inside the focus. The parabola goes around the focus. The focus is inside the parabola. The focus is underneath your directrix. So A is one of them. I'm just going to explain with the visual. Here's y equals 6 and here's 0, negative 6. So it's going to be going downward like that. Okay. A lot of these might do that. I apologize if so. B is going to be the same. B takes that look as well, where it's at y equals 2 for the directrix, and your focus is at 0, negative 2. So once again, your parabola is going to be going downward like that, so that also applies. So this is golden, this is golden. I know my explanations are not beautiful with this, so that works. On C, you notice the focus is at 0, 6. That's not a problem in and of itself, but the directrix at y equals negative 6 means that this thing is going to be focused, directrix, parabola opens upward into it. And I mean, that's really the explanation. The vertex is between the focus and the directrix. If the focus is above the vertex, then your parabola is going to open upward. So C does not apply for that reason, not C. And then D with your focus once again below, your directrix is above at 1, focus is below at negative 1, 0, negative 1. That's going to open downward as well. That's D. D also applies. So all three of those, A, B, and C, or A, B, and D apply. C does not apply for that reason. It's just the way that it opens with respect to the focus. Number 12, which of the following are possible coordinates of the point P in the graph shown? Explain. So, of the point P. Okay, well, let's see. Just based on where we are, this is the origin, and here's 0, negative 9. I imagine what they're saying is that the P is somewhere, it's in the positive x direction, negative y direction. So let's ignore ones that don't have positive x, negative y. That rules out A. That rules out D. And that's it. And after that, I guess what we're looking at are these sizes, I suppose. Oh, what we have to do is actually plug the values in, I see. So on number 12, again, we're ruling out A and D just because they're not the right values themselves. But let's find out this actual equation. It's a y equals ax squared equation that P value looks to be negative 9 because you would go downward 9 units from vertex to focus. That's what your P value is. Therefore, A is 1 over 4P or negative 1/36. So your equation is y equals negative 1/36 x squared. Now, why does that matter? Because we're going to substitute some of these values in. I'm going to plug in 3 and see what value I get for y. If it's this one, then it works. I'm going to plug in 6 and see if I get this for y, etc. We'll keep working that out. Or, I mean, forget plugging them in. Let's just do it kind of naturally, right? I mean, we're going to be doing the same thing, but I'm going to be doing 3 squared and then multiply. Well, yeah, okay. I guess that's what we're doing. So that's fine. So let's try B. So on B, we're going to get y equals negative 1/36 times 3 squared. 3 squared is 9, and that's negative 1/4. So B does check out, because that's the y value that we get. So B works. On C, we'll substitute 4. We get y equals negative 1/36 times 4 squared. 4 squared is 16. Negative 16 over 36 reduces to, you can divide by 4, right? Negative 4/9. And that's the value that they got right there is negative 4/9. So that one also applies like that. E, because A and D didn't work. So E, plug in 6. And here we're going to get negative 36 over 36, which is negative 1. And that's the value that they showed, negative 1. So that one checks out. So E works. And then lastly, F. We substitute 2 into there. Y equals negative 1/36 times 2 squared. 2 squared is 4. So negative 4/36 is negative 1/9. Negative 1/9. They have negative 1/18. So that does not apply. That's also no good. It's just B, C, and E. So you find out your equation using your 1 over 4P relationship. You then plug in those x values in there and see if you get the y out. These never would have applied just because x was not negative in this case. Oh, you know what? I take that back. A can potentially apply. In fact, I'm going to say that A works. A works. They're not saying that P is necessarily in the first quadrant. P can be anywhere on this parabola. They're just asking which ones work for the equation. D can't work because we're never going to be up above right here, right? When I plug in 1, the best I could get is negative 1/36. And in fact, I think you do. But A also works because E works, right? If E works, so does A. These are just symmetrical. negative 6 comma negative 1, positive 6 comma negative 1. So A actually does apply. So let me just put that. A, y equals negative 136 times 6 squared. That's also negative 1. So that does check out. I thought they meant specifically points in the fourth quadrant, and apparently that's not just that. It's just ones for this parabola, any xy. That does work. Okay, let's move forward. 13 to 20. Let's identify the focus, directrix, and axis of symmetry on the parabola, and we're going to graph the equation. Now, I'm going to begin with the graph probably on these. I want to make sure that that still makes sense on what these things are, and I'm going to go ahead and use these graphs for it. So on number 13, we have y equals 1/8 x squared. These vertexes are at the origin, so I'm going to go ahead and leave them there. So 0, 0. It's a y equals x squared equation. 1/8 is our vertical compression. Instead of 1, 1, we're going 1, 1/8. Instead of 2, 4, 1/8 of 4 is 1/2. 1/8 of 9 is 9/8, so 1 1/8. 1/8 of 16, 4 squared is 2. 1/8 of 25, I don't know how often I'm going to do every little point, but I'm going to do a lot of them that work. Maybe I will. 1/8 of 25 is 3 and an 8th, so 1, 2, 3 and an 8th like there. 1/8 of 36 is, see, here's the problem, now I got to do this, 9 halves, so 4 1/2. 4 1/2, like that. 1/8 of 7, see, I'm going to skip the 7, 49 eighths. I don't care. No, it's 6 and an 1/8. I guess I do care. 1/8 of 64 is 8. That looks good. So let's plot those points across on the other side. What's going to be nice about these kind of being drawn to scale is that we get to see the focus and directrix for their true distances and how they are. If this is as drawn to scale as I can make it, and focus and directrix get to go actually on the scale here, then we get to see points that are equidistant from these points anywhere on here. You'll see what I mean when we plot the focus and directrix. I need to draw a good looking curve to start with though, and I don't know if this is a good start. So here is that curve, very wide, and you almost hope that these are wide, because if they're not, I know it's harder to sketch the points on the graph, but if they're not, your focus and direction is going to become very tight fractions right here, and that's when it gets really weird. Plus, the graph is going to be very sharp. So your p-value, this is what's next, right? 1/8 is a, so a is 1/8. Now, just like a is 1 over 4p, p is also 1 over 4a. So p is 1 over 4 times 1/8, which is 1 over 1/2. And 1 over 1/2 is 2, so p is 2. If p is 2, that means your focus goes 2 units up from your vertex right there. It's at 0, 2. And your directrix is this line. It's the first time I actually get to draw a line using my tool here. It's the line y equals -2, like that. That is D. Y equals -2. And I'm just going to write it right there. Those are the two things. And that is your answer set. We got the focus, directrix, axis of symmetry. I didn't write that. Axis of symmetry is x equals 0. And it might be that almost every time, as long as it's all these vertexes seem to be at the origin. I think they're going to be to begin with. So your axis of symmetry goes up and down like that. I'm not drawing it, but that's what it is. So x equals 0. Now, the cool thing about this, like I stated, is that because these things are kind of drawn to scale in this way as well, that means that this distance and this distance are the same. Like I could actually grab a ruler and show that those things are the same as well. This distance and this distance are equal. This distance and this distance are equal. This distance and this distance are equal, things like that. Okay, so those are all equal just like that. And it's drawn to scale as such, which is kind of the cool part about it. I don't have to do that each time. It's just something that's neat that now you actually get to apply those. Number 14, y equals -1/12 x squared. 14, y equals -1/12 x squared. So let's get a parabola in here. Negative means we're going to go upside down. The 1/12 is we get to take 1/12 of our values. 1/12 of 1 is kind of 1/12 of 4 over 2 down 4, but a 1/12 of that is 1/3. So we're going to go down a third, and on this side. 1/12 of 9, if I go 3 over, is at 3/4. Fine, I'll put the 1/12. 1/12 of 16 is 4/3. So this is going to be kind of hard to put. 1/12 of 25 is a little more than 2.5. No, excuse me, it's a little more than 2. It's 2 1/12. And 1/12 of 36 is 3. So again, we're going over 6, down 6 squared. That's down 36, things like that. 1/12 of 7, that's 4 1/12. Excuse me, of 49, 7 squared. 1/12 of 64, I don't actually know that. 5 1/3. 5 1/3. 1/12 of 81, 7 3/4. If I did that right. No, 7 8/4. 6 3/4. 6 3/4. And 1/12 of 10, I don't know. They said sketch the graph, and I'm more to scale than any of you guys would ever dream to be, at least within that time frame. Okay. That's the one problem about these fraction things, though. Okay. The p value, it's going to be negative. I mean, we're going to establish it as negative anyway. Remember, this is a. So p is 1 over 4a. 4 times negative 1/12 is negative 4/12, or negative 1/3. 1 divided by negative 1/3 is negative 3. So p is negative 3, which means we go 3 units down to get our focus, which is at 0, negative 3. And our directrix will be 3 units up right here. The directrix will be at y equals positive 3. Now your axis of symmetry, once again, is x equals 0. Just like that. So those are the sets of values. Number 15. Some more on that stretch factor. Compression factor, if you will. X equals negative 1/20 y squared. Okay, so for these graphs here, an x equals y squared either opens up left or right. In this case, because the a is negative, it's a horizontal stretch or compression, it's going to open to the left. But the vertex is still at the origin like this. Now for your 1, 1, 2, 4, 3, 9, it's going to look like this in that direction. And we're going to horizontally compress some things. We're going to divide these numbers by 20. So, 1/20th, 4/20ths, 9/20ths, things like that. A lot of these aren't going to be very easy to put very well. So 1/20th is like, you can barely fit it. 4/20ths is 1/5, can still hardly fit that here. So 1/20th and 1/5 is right there. 9/20ths is about a half, close to it, just underneath. 16/20ths is 4/5, so looking more like that. Again, it's really hard to judge this. And 25/20ths is 1 1/4. 36/20ths, again 6 squared. 36/20ths is 1 4/5 up here. 7/20ths is about 2 1/2, just a little bit less than that. It's 2 9/20ths. 64/20ths is 3 1/5. 81/20ths is 4 1/20th. So pretty much right by 4, like that. And then 100/20ths is 5. So we're going to be able to hit that right there. So it'll look nice if I could draw a nice curve through it. Close. There's the first half of it. Let's see if I can make the second half look any better. That second half looks pretty clean. That first half, I don't know, not quite as clean. But that looks pretty good, huh? All right, there's the graph. Now, as far as P goes, and listen, what I've been doing is P is 1 over 4A, and also A is 1 over 4P. And the reason why I bring this up is because you can do this as well. Here's your A value, negative 1/20th. I could say negative 1/20th equals 1 over 4P, and I could cross multiply. So 4P times negative 1 is negative 4P equals, 20, and divide both sides by negative 4. You get P equals negative 5. I've been doing instead, like this, 1 over 4 times negative 1/20th, which is 1 over negative 1/5, which is then negative 5. So whichever way you prefer is up to you, the cross multiplication thing or not. Just make sure the negative only applies to one portion of it. But P is negative 5 means this is where your focus is right there. That is at negative 5 comma 0. Your vertex is at the origin. Your directrix will be this vertical line this time. It's outside of the parabola right here. The directrix is x equals 5. It goes that way. Your axis of symmetry is the x-axis this time. Your axis of symmetry is the y equals equation. It is y equals 0. And those are your values for number 15. And once again, the wider it is, the farther apart these things go. This is 5 and this is 5 right there. But also, as you look, this would be the same distance away as that, all that kind of jazz. Okay, number 16. The numbers just get bigger. X equals 1/24 y squared. So, I think these problems are going even longer than the distance formula ones. So, x equals 1/24 y squared. Vertex is at the origin, and it's an x equals y squared equation, so it's going to be going to the right because it's a positive a value. You get 1/24 of 1, which I really can't plot at all. I mean, it's whatever. 4/24 is 1/6. Once again, it's pretty low. 9/24, oh gosh, 3/8. Still less than a half. More so than 9/20. 16/24 is 2/3. And hopefully you know where I'm saying these numbers. That's 4 squared. 4 squared is 16. 5 squared is 25. 25/24 is 1 1/24. So like that. 36/24 is 1 1/2. 49/24 is 2 1/24. 64/24, I don't know what that is. 8. 8/3, 2 2/3. 2 2/3. 81/24 is 27/8, which is 3 3/8. 3 3/8 right here. 100/24, I don't know, 50/12, 25/6, 4 1/6. 4 1/6. So out there. As much as I'm going to be able to fit there. Okay, here's this nice wide parabola. And I don't know how much they actually want that to scale, but because the other ones need to be to scale, because I saw them kind of like this on the examples, I'm going to go ahead and do that. I'm just going to talk about how you can get each individual problem or number. I'm sure they can do the same with a table. It works that out. Let's use that proportion version as before. A is 1/4p, so 1/24 is 1/4p. So 4p is 24, and p is 6. So again, you can go that way. 6 in from there is your focus. That's at 6, 0. Your directrix is going to be 6 units away on the other side. Is this vertical line like this? That's going to be the vertical line x equals -6. And your axis of symmetry, the x-axis, is y equals 0. Still 4 more of these to go, and hopefully they shrink. Oh, that does not shrink. Not at all. I don't even know what I'm going to do with that one when it comes to stretches and such. They're really testing my patience on this one, guys. This is going to be a long video, I'll tell you what. It's going to test how much video memory I even have. Number 17, y squared equals 16x. Let's divide both sides by 16. You'll get x equals 1/16 y squared. So this is the equation we're going to base our graph off of here. So here we go. Vertex is at the origin. It's an x equals y squared equation, so it's going to go to the right. You're going to take 1/16 of 1, which is 1/16. 1/16 of 4, which is a quarter. 1/16 of, 9/16 is, that's a little more than half. 16/16 is 1. 25/16 is 1 9/16, so a little more than a half there again. 36/16 is 2 1/4. 49/16 is 3 1/16. 64/16 is 4. And I'm going to stop right there. Those are good. 81/16, no, I'm not. 5 1/16. There we go. Now I'm going to stop right there. 100/16, I don't even know. I'm going to stop right there, though. That's pretty good. Once I hit that 4, I felt good about things. I'm glad they didn't make it like 17 or something really strange where I can't even reduce the fractions. I wouldn't even know what 13/17 or something like that would become. You know what I mean? Okay, I'm going to go back to the other way that I did this before. P is 1/4a, so 1/4 times 1/16. That's 1/4 1/4. Excuse me, 1/1/4, which is 4. So we're going to go 4 units away over here. That's at 4, 0. That's your focus. Your directrix is the line x equals -4 over here. It's a vertical line. And your axis of symmetry is the x-axis, otherwise known as y equals 0. Okay, number 18. Negative x squared equals 48y. If I divide both sides by 48, oh boy. Oh boy. Negative x squared equals 48y. Let's divide both sides by 48. You'll get y equals -1 over 48x squared. Okay. I'm not going to be able to plot when x equals 1. Probably when x equals 2. So, vertex at the origin, y equals negative x squared. It's going to go downward. Over 1, down 1/48. No. Over 2, down 4/48. That's, excuse me, that's down 1/12. Still pretty much no. I'm going to plot it very small. Over 3, down 9/48. It does reduce. It's 3/16, which is less than a quarter. Over 4, down 16/48, and that's a third. Over 5, down 25/48, a little more than a half. Over 6, down 36/48, that is 3/4. Over 7, down 49/48, that's just 1 1/48, -1 1/48, like that. Over 8, down 64/48, that is 1 1/3. Over 9, down 81/48, that's less, I don't know what that is. And 100/48 is just a little more than 2. So I'm just going to just do it like that. Whoops. It's a little more than 2 like that. So barely even has any stretch. I don't even think I got these to scale very well here. So I'm just going to do the best I can. Hey, they say draw the graph. Yes, I could have changed my scales, but I don't think that's really my plan right now. Okay, so there's the there's the parabola. Sure. Okay. P is 1 over 4a. That's 1 over -1/12, so you get -12. Now, my focus is down here. That I can't even fit that one, so I don't want to change the scale too much. The focus, I don't even think they asked me necessarily to plot the focus on the graph though, right? But you do need to know the ordered pair. It's 12 down, so 0, -12. And then your directrix is all the way up here at y equals 12. So D is y equals 12. The axis of symmetry is the y-axis this time, so AOS, which I'm not drawing, they said identify, is x equals 0. X equals 0. But those are your values that we're getting out from that. Okay, number 19. 2 more on this set. 6x squared plus 3y equals 0. Okay, at least this will be much more normal looking for me. I'll feel much more comfortable drawing this graph and such. 6x squared plus 3y equals 0. We can, I'm going to subtract, so we got to solve for y, right? 3y is -6x squared, subtract that over, divide by 3, and you get y equals -2x squared. This will look a lot more normal, but you're not going to be as happy about your focus and directrix. I guess you're like, oh, well, I'm willing to take the hit. Y equals -2x squared, it's going to be a downward facing graph, vertex at the origin. We get to go 1, 2, and 2, 8. Remember how normal those were? And you're like, yep, I'm going to take that hit. Now, this does come at the cost of a closer focus in directrix, and even fractionally so. This is where, when you do IM3, we're going to probably hit a lot of those that will be more so fractions, and they're just not as fun to do, especially when it's off the vertex is off the origin. Your P is 1 over 4a. In this case, you probably want to leave it like that, and that's -1/8. We're going to go 1/8 down. See, this is how short this is. Your focus, even though they're not asking you to necessarily plot it, your focus is down at 0, -1/8, like that. Your directrix is this line that gets really close to this right there, 1/8 above. So that's at y equals 1/8, just like that. Now your axis of symmetry is still x equals 0, like that, but that's what you get, right? That's just what it looks like. That's the cost of doing business with a more normal looking thing right there. And lastly, number 20. You see, this time I'm not going to be able to plot the focus in directrix, same way as the other ones got a little weird. you got 8x squared minus y equals 0. If I add y to both sides, I get y equals 8x squared. Right? That becomes positive just like that. So it's a y equals 8x squared equation. This graph goes upward. It goes super tall, stretches with 8. Vertex is right here. And over 1 up 8. Over 2, you would go up 32 because that's 8 times 4. That's just super duper tall. So this goes back to one of these kinds of things where you might say, hey, use the tall graph. Well, my tall graph doesn't go to 32. And the other problem is if I want to do my focus in directrix any form of justice, I'd have to get it as close to looking like this as I can. It's not going to do any justice, though. What's your focus? It's based on P. 1 over 4a, which is 1 over 32. Your focus was basically, I can't really plot them. I'm not going to be able to. But your focus is up from the origin. So your focus is at 0, 1 over 32 as an ordered pair. Your directrix is going to be y equals, it's a horizontal line just above, or just below. Y equals negative 1 over 32, like that. Your axis of symmetry is x equals 0. Okay, that's some sniffles. Let me pause for a second. Sorry, it was from that previous sneeze. Okay, that was a lot of graphing. Let's go ahead and take a look at what they have for error analysis on 21 and 22. Describe and correct the error. We have negative 6x plus y squared equals 0. They have a focus here and a directrix here. Okay, well, let's go ahead and see what's going on. I'm not going to look at the graph itself yet. I'm really going to look at that p stuff. So 21, negative 6x plus, because I don't know what the actual error is just yet. I assume it's the points. But let's start correcting it. Let's get x by itself by subtracting y squared. I divide both sides by negative 6, and I get 1/6 y squared. So the problem is, in this thing here, the 1.5 may be correct, actually. Let's see. P is 1 over 4a, which is 1 over 2/3, which is 3/2, which is 1.5. So the p-value is good. There's no problem with that. The problem is this is an x equals y squared equation. I actually should have seen that off the bat. It's an x equals y squared equation, and that means that it should be a rightwards facing parabola if a is positive, which it is. So the problem is just the way that this graph is facing here. This is an x equals y squared equation. So the graph, and it's a positive y squared. So the graph should be facing right instead of up. Correct it. I mean, I'll do the rough sketch version. I'm not going to do the actual 1/6 portion right here until they ask us to, they said correct the error in graphing the parabola. Oh, I guess they did say graph it. Okay, fine. So I'm going to graph this thing. Let's correct it. We got x equals 1/6 y squared. Their p is correct. It just kind of works in this other way. So over 1, or up 1 over 1/6, up 4 over 1/6 of 4, which is 2/3, up 3 over 1.5, that's 9/6. Let's go and reflect those ones across. 16/6 is 2 and 2/3. 25/6 is 4 and 1/6. Wait, that's not right. That's 3 and 1/6. 4 and 1/6. 36/6 is 6, and that's gonna be good enough for me for right there. For what I want out of it. Once I hit the integer, I feel just better about things, better about my life. Okay, the 1.5 would have been the focus, so 1.5 comma 0. And then the directrix is going to be at x equals negative 1.5, like that. Directrix x equals negative 1.5. Okay, that's correcting that error on number 21. Number 22. Maybe the same kind of thing on how it faces. Sort of. So number 22. Let's see if the focus in directrix is a problem. 0.5 y squared plus x equals 0. I'm going to get x by itself by subtracting 0.5 y squared. You get negative 0.5 y squared. And by the way, 0.5 is the same as 1/2. So x is negative 1/2 y squared, like that. Now, the thing is, it's an x equals y squared equation, but it's an x equals negative y squared equation, which means the graph should have went left instead of right. let's confirm that the p-value is as supposed to be. P is 1 over 4a, which is 1 over negative 2, which is, negative 1/2. So they seem to be having that thing. They had 1/2. They went kind of the wrong thing. They didn't get x by itself or whatever. So although they have an x equals y squared equation, the graph, the a value is negative instead of positive. So the graph should open left instead of right. So let's go ahead and graph that. Negative 1/2 y squared. That's a decent compression, which we can work off of. So negative 1/2 y squared, vertex is at the origin. We're going to open left. Up 1 over 1/2. Up 2 over half of 4. These are in blue. Up 3 over half of 9. Up 4 over half of 16. And let's reflect those across the axis of symmetry. Just like that. Okay. I don't know if sideways parabolas are easier for me to draw the curve for than the other one. Sort of, maybe sometimes. Especially going, spoke too soon. Probably not. Are these not to scale? I'm always doing something right there. I think something's happening on my tablet right there. I'm not quite sure. That was kind of weird. The p-value was 1/2, so it's going to be 1/2 way in right there, and then that's the focus, and then the axis of symmetry is going to be over here. So obviously those are flip-flopped when your p-value is negative and such, and you should really treat that negative for how it is. So the focus is going to be at negative 1/2 comma 0, and this is going to be directrix at x equals positive 1/2, so 0.5 like that. Okay. And that corrects 22. Let's go and look at 23, analyzing equations. The cross-section with units in inches of a parabolic satellite can be modeled by the equation y equals 1 over 38x squared, kind of an obscure number in 38. How far is the receiver from the vertex of the cross-section? Explain. Cross-section. I don't know what the receiver is. Is the receiver like the top? Is the receiver Is the I don't know what the receiver is. Let me find a satellite dish from a previous example. There are some things there. Let's see if they ever mention the word receiver. They talked about an engine up here, so I don't know if the receiver is the focus or not. They don't really mention on these problems. Let's go back. Let's see. Sorry about this. The cross-section of a parabolic satellite can be modeled by the thing. How far is the receiver from the vertex? I don't know what a receiver on a satellite dish is. Okay, I'm gonna assume it's the focus. I'm just gonna assume it's the focus. So on number 23, we have, a satellite dish, modeled by this guy right there. Boop, 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 boop. And then the receiver, I imagine, is just this guy right here, boop, 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 which is the focus and the receiver. E-I-V-E-R. So this is y equals 1 over 38x squared for just this guy right there. Okay. Hopefully they're not talking about like right there. Okay. So I'm actually not really sure. So if they're talking about that, your A is 1 over 38. So P is 1 over 4 times 1 over 38. Sorry if this isn't the receiver. So that's 2/19. 1 over 2/19, which is 19 over 2. 19 over 2 is also 9.5. Now this whole thing is the units are in inches. So this guy here is at 0, 9.5. So the receiver, based on my thing, the receiver is 9.5 inches from the vertex of the cross section. Okay? I hope that that's right. Okay. Number 24. The cross-section of a parabolic spotlight can be modeled by this equation here. Boom. How far is the bulb from the vertex of the cross-section? I mean, this is the bulb, right? So I don't know, if that's the focus in what they're talking about. But you know what? I'm really bad at these word problems because I don't know if they're just referring to the focus as that little point. I guess. How far is the bulb from the vertex of the cross-section? Okay, yeah, I'll pretend like the bulb is the, I'll pretend like it's the focus again. So this is an x equals y squared equation, so now it's going to look like it goes this direction, what have you. So here's your 1/20th y squared right there, and there's a bulb, which is the focus right there. So x equals 1/20th y squared. So your a value, once again, being 1/20th, p is 1 over 4 times 1/20th, which is 1 over 1/5. Which is 5. So your focus is at 5, 0 compared to the vertex at the origin. This thing's in inches, so the bulb is 5 inches from the vertex of the cross-section. 5 inches from the vertex. Sounds good to me. Okay. In 25 to 28, write an equation of the parabola as shown. Okay, so numbers 25 to 28. This time you have information based off the drawing. So there are a couple things I'm going to do with this thing here. We are going to determine what kind of equation it's going to be based on the way that it faces. On number 25, this will be a y equals x squared equation. Okay, now these vertexes are also on the origin, which helps. All we need to do is find a. We need to find out a. So a is based off of p. Now, y equals x squared, I literally mean it's a positive x squared. It's not negative x squared. If it's the other way, I'm going to say y equals negative x squared. But a is a positive number. Whether or not I knew that, or it's not something I really care about. And p, I can make positive based off your focus being here. If your vertex is at the origin, and your directrix is at y equals negative 8, your focus is going to be at 0, 8. Basically, it's going to be 8 units away there. So your p value is 8. Instead of accidentally putting negative 8, because of the directrix, p value is 8. A is 1 over 4p. So 1 over 4 times 8. So p is 8. A is 1 over 4 times 8, which is 1 over 32. So this equation will be y equals 1 over 32x squared. So those are basically the two things we have to do. Figure out what kind of equation you have based on the signs and such. Figure out p, and use that to figure out a. Number 26. We have y equals 3/4 as our directrix. That means our focus goes down here. It is a y equals equation for our parabola because it goes upside down. It's a y equals negative x squared equation. So, when you get your a value, basically, just know that your a value is going to be negative. Even if you called p positive. Like, watch this. Guys, I'm going to call p 3/4. It's negative 3/4, but I'm going to call it 3/4, okay? So a is 1 over 4p. 4 times 3/4 is 3, so that's 1/3. So it's going to be y equals negative 1/3 x squared. Look, I already know it's going to be a negative x squared equation. I already know that this thing goes downwards. That's kind of why I'm saying it doesn't really matter if p. I mean, it does. But if you can acknowledge for yourself what you're going to do, what's the point of p? To find a. Or to find your focus in directrix. As long as you know the direction to go, you're fine. I can still write the equation properly, and that's all I care about. Okay. This one, your p value is going to be 5/2, negative 5/2, because this is an x equals y squared equation, but more importantly, it's an x equals negative y squared equation. A will be negative. P is 5/2, yes, it's negative 5/2. So a is going to be 1 over 4 times 5/2. 5/2 of 4 is 10, so this is going to be 1/10. So your equation will be x equals negative 1/10 y squared. It does go to the left, it does make it negative. So hopefully that makes sense whenever I say that, guys. If I ever do say p is a positive number when it's truly negative, you're going to have to go with me on what I'm going to do with it. P units to there is the focus. It's inside the vertex. I know that p is negative. I understand I'm going to go to the left. That kind of thing. And then number 28, x equals negative 2 right there. Vertex is at 0, 0. So p is going to be 2. This is an x equals positive y squared equation with the p value of 2. And it is indeed actually 2, not negative 2. A equals 1 over 4p, which is 1/8. So this will be an x equals 1/8 y squared equation. Okay. And that's 25 to 28, the 4 fastest problems we've had so far. In 29 to 30, 36, we're also going to write equations. This time we're not given the graph. We are given just information, but we might want to draw a graph based on it. Let me take care of more sniffles. Okay, number 29. 3, 0 is your focus. Your directrix is x equals -3. So far, we haven't moved off the origin, and it seems like that hasn't happened. This won't still happen soon here. So your focus is at 3, 0. Your directrix is at x equals -3. All I care about, I don't have to label everything. All I care about is which way the graph goes and what p is. So the same stuff as before. Just look at what it looks like. This is an x equals positive y squared equation. The p-value will be 3. So a is going to be 1 over 4p, or 1/12. So this will be x equals 1/12 y squared. It's an x equals y equation because y squared equation, because the way that it opens up, it's positive, and it looks like that. Number 30. Your focus is 2/3, 0. Your directrix is x equals -2/3. This once again opens the same direction as before. Hopefully you can kind of recognize that focus, once again, is here. Directrix is there. Positive, negative. We're going to open that way. X equals y squared equation. This time your p is going to be 2/3. So a is 1 over 4 times 2/3. 1 over 4p. That's a little bit different. This is going to be 1 over 8/3, which is 3/8. Which is fine. So a is 3/8. This will be x equals 3/8 y squared. Hold on, I'm going to check my phone really fast here. So my phone was getting notifications. It was vibrating and telling me that I have a robot vacuum in my classroom, and it was telling me that it was doing scheduled maintenance, and it finished. So I finished cleaning my classroom. My classroom, I have it clean it up because my kids are a mess. Kids come in for lunch and stuff too. Number 31. I'm sure part of it's my mess. Number 31. Directrix is x equals -10, and the vertex is at 0, 0. So make sure you don't think that that's the focus, which it very well could have been. But the directrix is over here. Vertex is right there, which still means this is the focus going over that, which means, this is the way that the graph goes. But regarding p-value, the p-value here is, this is -10 right there. But the p-value going this way to the focus is 10, right? It's positive to the focus, which, it's an x equals y squared equation. Once again, x equals positive y squared. P is 10. So your a value is 1 over 4p, which is 1/40th. So your equation will be x equals 1/40th y squared. Number 32. This time it's a directrix. It's a y equals equation. So number 32. You have directrix, and sorry that I'm not copying these things down again. I guess it's habit for me to label. Oh, I'm not really labeling them either. So I probably should, but the directrix is y equals 8/3. I'm better than that. Here's your directrix, and your vertex is at the origin. This graph has to go downward to go away from there. This is a y equals -x squared equation. Now the directrix is 8/3 away from there. Your focus would be 8/3 the other direction. So your p-value is -8/3, and it is actually negative, just like the a value is going to be. So a is 1 over 4 times -8/3. That's your p. And that's going to be 1 over -32/3. So that's -3 over 32. So, okay, that's your a value. So your equation will be y equals -3 over 32x squared. Very bizarre, very bizarre. And I'm glad I don't actually have to graph that thing with scales and all, but that's it. Number 33, this time we have the focus and directrix once again, but they are going to be in some different spots here. This time your focus is at 0, -5/3. Boom. Your focus. And your directrix is at y equals +5/3, which makes your vertex at the origin, once again. And we are going to get some problems where vertex isn't at the origin. They clearly showed that's going to be happening later. We'll see when that shows up. It's a y equals -x squared equation, just like before. Your p-value is -5/3. -5/3, and a is 1 over 4 times -5/3, which is 1 over -20/3, which is -3/20. Your equation is y equals -3/20 x squared. Three more of this variety. We have number 34, or focus at 0, 5/4. And directrix at y equals negative 5/4. This graph will face upward. Focus is up here at 0, 5/4. Directrix y equals negative 5/4. Vertex is right in the middle at 0, 0. Your p-value from 0, 0 to 0, 5/4 is 5/4 for the y equals x squared equation. P is 5/4, so A is 1 over 4 times 5/4. Yes, I'm going kind of fast here. That's 1/5. So this will be y equals 1/5 x squared. Number 35. Wait, what do my problems go to? 54. Okay, not even 2/3 done. And we hit some word problems later. Number 35. My neck. I keep doing that because I have a crick in my neck. I even hear it crack. Focus is at 0, 6/7, and there's a vertex at the origin. What else is new? So there's your vertex. Here's your focus, which means your parabola goes upward. Your p is 6/7. So it's a y equals x squared equation. P is 6/7. A is 1 over 4 times 6/7, which is 1 over 24/7, which is 7/24. That does not reduce. This is going to be the equation y equals 7/24 x squared. I don't know who makes these problems, like the individual people, but I don't know who this person was that was like, you know, I want to do another problem. Let's make it this one. Let's make that a value 7/24. Yay. And then, you know, like that. I mean, at some point they're like, oh man, these are not fun to write. They probably like writing the book, and they probably like writing some problems, and then after that they're like, oh man, I don't know how creative I can be. I gotta make these different problems. Focus is at negative 4/5, 0 over here. That's your focus. Vertex is at the origin. This graph is going to go to the left. So it's going to mean x equals negative y squared equation once again. Going back to that. It's 4/5 away. So the p-value is negative 4/5. And your a value is going to be 1 over 4p, 1 over 4p, which is 1 over negative 16/5, which is negative 5 over 16. So your equation will be x equals negative 5/16 y squared. Okay, there's that set in writing equations. I have to sneeze again. I'm going to pause. Oh, that sneeze took a toll on me. I'm probably going to be nasally now. Thing is, I'm not even sick. It's allergies from... I opened my door in my classroom the other day, and I often don't do that. My windows, and there's a tree with some pollen that blows in. I was trying to let in some air. It just did not work right. So that was a problem. So you're going to hear some sniffles again. My apologies. Okay. Number 37. Okay, write an equation of the parabola shown. Okay. Now we have some changes on the vertex, and that's important to note. We got to know what that vertex is. I'm going to be writing this one down. These are scaled by 2s on this problem. I got to notice that. I think 2, 4, 6, 8, 10, 12. So the vertex on this problem is negative 4, 0. That is an h and a k. This is an x equals y squared equation, but specifically it's x equals negative y squared. I don't know what a is just yet, but as far as we know, it's x equals a times y minus k, quantity squared plus h, like that. And y minus 0 squared is just y squared. So we know it's going to look like this. ay squared minus 4. That's going to be the cleaned up version of it. The focus is, it's not 2 units away. Remember, these scale by 2s. It's 4 units away. So the p-value is negative 4. It's 4 units to the left. It's an x equals negative y squared equation. So the p-value, in this case, is negative 4. A is 1 over 4p, which is negative 1/16. So your equation, this equation is going to be negative 1/16 y squared minus 4 for an x equals format. They didn't give us the directrix, right? They just gave us the vertex and focus, and that's what they're giving us for all of them, but the p-value is the distance from the vertex to the focus. Number 38. These are scaled by 1s this time, so this time your vertex is at 4, 1. It's an x equals positive y squared equation, x equals y squared. So at this stance, my equation, well, I'm not going to say at this stance what it is. Let's just see. The p-value is 2. The focus is 2 away from the vertex in the right direction over there. So A is 1 over 4 times 2, which is 1/8. So listen, the equation is going to be x equals A times y minus k, quantity squared, plus h. And that is the equation. So remember, or if you were here with me for the lecture portion, x equals y squared equations, the k is on the inside and is flipped, the h is on the outside and stays the same. So it's the opposite of what you would have in those other things. I wish they had normal ones first, like numbers 39 and 40, ones that you'd be familiar with in those instances. Your vertex here, these are scaled by, that's scaled by 1/2. So your vertex is at 0, 1. That's not 0, 2. Look at that. This is 1, 2, 3, like that. Your focus is 1.5 away. So the p-value is 1.5 or 3/2. But this is going to be a y equals x squared equation and a positive one. P is 1.5 or 3/2. A is 1 over 4 times 3/2. 4 over 2 is 2 times 3 is 6. So we get 1 over 6. So this equation will be in raw form, y equals A times x minus h quantity squared plus k, or y equals 1/6 x squared plus 1. And that is number 39. There we go. And then number 40, these scale by 2s. Yep. They really want to test you on your scaling here. The vertex is at -6, -4. That's your HK. It is a y equals -x squared equation. Your p-value, the distance from vertex to focus, remember these go by 2s, so this will be 2, 4, 6. The p-value is -6. So for your A value, your vertical stretch, that's 1 over 4 p, which is -1/24. So my equation, being a y equals x squared equation, will be y equals -1/24 is A times x minus h quantity squared plus k, like that. Okay, those went a little faster. 41 to 46, we identify vertex, focus, directrix, and axis of symmetry. Describe the transformations of the graph of the standard equation with p equals 1 and vertex is 0, 0. Let me do some snifflies. Okay, so the first one, so we're not graphing them. I might have to use parts of the graph to make some things happen, but 41, we have y equals 1/8 times x minus 3 quantity squared plus 2. They want vertex, focus. So the vertex, we'll do these in blue. The vertex is at 3, 2. It's a y equals x squared equation. X minus h is 3, k is 2, right there. Focus and directrix, I'm going to get with p. My axis of symmetry, I'm going to write right now. That's fine. Axis of symmetry is x equals 3. For the focus and directrix, I need to get p. Here's a. So p is 1 over 4a. That's 1 over 1/2, which is 2. Now, here's the part where a graph can help. This is the only time I might do this visual. Other times I might not. Or this is the only time I will do the visual. Other times I might not. Your graph is at 3, 2. Boom, right here. 3. Oops. Well, I might do them again. 2, at 3, 2, this graph goes upward, right? Your p-value is 2, which means your focus goes 2 up from here. Your focus is at 3, and 2 up from, 2 here is 4. And then your axis of symmetry is 2 down from there. Not your axis of symmetry, your directrix. That's at y equals 0. So, it might be helpful for me to include those visuals. I might even use an actual set of graph axes from that. But p being 2 is, if the graph goes upward, the focus is 2 inside of here. And remember, they have a formula for that. They're like h, k plus p and all that. And I get it. But you just got to go 2 up from your point. So instead of 3, 2, you're up at 3, 4. Instead of y equals 2, you're down at y equals 0 because of the p-value. So that's what your focus is. I labeled it already, but I'm just going to do it again. 3, 4. And your directrix is at y equals 0. Those are the 4 parts I needed. Describe the transformations of the graph of the standard equation with p equals 1 and vertex 0, 0. It's interesting they say p equals 1. So if P equals 1, keep in mind, P equals 1 means an A value, 1 over 4P, it's 1/4. So instead of 1/4, well, you know what? We can use P to talk about that instead, I suppose. I'm trying to think. If A was 1/4, now it's 1/8, right? P was 1, now P is 2. So if P gets doubled, A gets halved. So that kind of works in that way. So I don't really have to compare 1/4 to 1/8. I can compare more P this way. If P gets doubled, A gets halved. So that's kind of good for me to know. So that means my transformations, I'm going to start with that. I'm going to say, compared to a normal vertex 0, 0, and P being 1, because P is now 2 instead of 1, you vertically compress by a factor of 1/2. And then you translate 3 units right and 2 units up. That's how the vertex part works. No reflections. And you know why they say, well, I was going to say, you know why they say P instead of A? I think just because you can do that part easier. But also I thought they were going to talk about because X equals Y squared. And I don't think that matters. A is still an A on the other problems. But we won't have to say rotate or anything like that. X equals Y squared equations can still have a P of 1 and a vertex at 0, 0. So just compared to those other ones, they just say, without transforming them, what do you do? Or, sorry, with the untransformed graph, how do you transform it to get there? All right, number 42, y equals negative 1/4 times x plus 2 quantity squared plus 1. Let's start with the vertex here. It's a y equals x squared equation. Once again, it's a negative x squared. We'll have to be careful on that. So this is negative 2, 1 for the vertex. The axis of symmetry is going to be, let's do this in blue, is going to be at x equals negative 2. X equals negative 2. Let's get the P value. P is 1 over 4a. That's 1 over negative 1, which is negative 1. If we saw this graph, this is going to be an upside down facing graph like this. This vertex was at negative 2, 1. The P being negative 1 means we're going to, for the focus, we're going to go 1 down from here. So instead of negative 2, 1, we're going to be at negative 2, 0. For the directrix, we're going to be up here at y equals 1 up from negative 2, or 1 up from 1, which is 2. So y equals 2. So your focus is going to be at negative 2, 0. And your directrix is going to be at y equals 2. Pause one more time. Okay, so from there we describe our transformations. Because P is negative 1, A basically changes sign as well from being a 1/4 now to a negative 1/4. So it's not a stretch or anything, but you reflect. You reflect over the x-axis. Reflect over x-axis whenever it's a y equals equation. We're going to do something for the other way. And we're going to translate 2 units for the vertex, 2 units left and 1 unit up. So 2 units left, 1 unit up. Those are the transformations in comparison to there. That's number 42. Okay, number 43 is an x equals equation. So x equals 1/16 times blah, blah, blah. So let's look at that. Number 43, x equals 1/16 times y minus 3 quantity squared plus 1. Now the vertex, this is where we got to start being careful, because now as an x equals y squared equation, this is h, this is k, and h is the same value here. It is 1, k is the opposite, it is 3. Your vertex is at 1, 3, like that. Your axis of symmetry is now on the, it's on the y value here. It's going to be at y equals 3 instead. It's not an x equals equation anymore because it's a sideways parabola and it cuts through there at y equals 3. As far as P goes, that's no different. That's our 1 over 4a. Our a is 1/16. Although it's a horizontal compression factor, it still marks P. 1 over 1/4, which is 4. However, now as we look at this graph here, keep in mind, our vertex at 1, 3, great, looks like that. It's an x equals y squared equation, though, so it goes this way. So your vertex at 1, 3, your p-value being 4 means we're going to go 4 to the right from 1, 3 for your focus. 4 to the right of 1 is 5. It's at 5, 3. And your directrix is not only 4 to the left over here, but it's an x equals equation. It'll be x equals, and 4 left of 1 is negative 3. So your focus is going to be at 5 comma 3, and your directrix is going to be at x equals negative 3. So those are those 4 guys right there. As far as transformations go, they already account for the fact that it's an x equals y squared equation. We don't have to say anything on that. We just got to say the 4. So it's p is 4 instead of 1. So p is 4 times larger. That'll make a 4 times smaller. So and it's a horizontal compression. You horizontally compress by a factor of 1/4, and you translate 1 unit right and 3 units up. That's just how the vertex works. So that's fine. 3 units up like that. There are those descriptions. Number 44. Y equals, back to kind of a normal one, and then we have a couple x equals at the end. So y equals x plus 3 quantity squared minus 5. You can't see the a value, but it would be a 1, so I'm going to go ahead and write that. Your vertex is at negative 3, negative 5. Your axis of symmetry, back to a y equals x squared equation, it's going to be an x equals thing, and x equals negative 3. It's going to be the h. Your p is going to be a standard, well, to me it's standard, 1/4, because a is standard, so 1/4. Oh, but this is where we have to hit some fraction things, so this is where it gets a little, too bad. We're going to have to deal with getting a common denominator and stuff like that. If you want to be particular, we can use decimals, but I'll give you more than one version of this answer if you need it. So negative 3, negative 5 is your vertex here. Vertex at negative 3, negative 5. This graph goes upward, because it's a y equals positive x squared like this. Now your 1/4, your focus is going to be 1/4 up from negative 5. So it's at negative 3, comma, and then we got to do negative 5 plus 1/4. So here's where I'm going to do some work. Negative 5 plus 1/4, that is negative 20/4 plus 1/4, which is negative 19/4. This is one version of that answer. So let's write this underneath. F is there. So one version of the focus we can write, I'm going to write a few of them. So we can either write negative 3, comma, negative 19/4, or we can write negative 3, comma, negative 4 and 3/4, or negative 3, comma, negative 4.75. Any of those ones are valid because 1/4 is also 0.25. And I see more people are probably most common with that one. Mixed number could happen, I suppose. The directrix goes the other direction. It is downward. So 1/4 down from negative 5 would have been negative 21/4. So negative 5 minus 1/4 is negative 20/4 minus 1/4, or negative 21/4, like that. So your directrix is either y equals negative 21/4, or y equals negative 5 1/4. I don't really like that one. Or y equals negative 5.25. Yeah, mixed numbers aren't really a big thing that we do anymore. I mean, as far as me saying the number, well, I mentioned them, right? I mentioned them when I was doing the other graphs of the scales, but I don't really write them. We don't really write them that way. We stick to decimals and improper fractions when we can for answers. That's totally accepted. As far as the transformation goes, this is the p-value by default is 1. Now it's 1/4, 4 times smaller, which means a is going to be 4 times larger than the traditional 1/4 that they're saying. So we are going to vertically stretch this by a factor of 4. And we are also translating 3 units left and 5 units down. I don't know if they're asking us to describe transformations of vertex and focus and stuff like that. I sure hope that they're not asking us to do that. They said of the graph. The graph does not include the focus and directrix. Those are features describing the points on the graph. So I think we should be fine. Number 45, x equals y squared, but it's a negative y squared. So 45, we're going to get x equals, what did I just do? X equals negative 3 times y plus 4 quantity squared plus 2. Again, an x equals y squared equation, we have to be careful. Your h is here, your k is here. So your vertex is at 2, negative 4. Your axis of symmetry is a y equals equation. It's going to be y equals negative 4. Okay, let's come up with the p-value. P is 1 over 4a, so 1 over 4 times negative 3. So it's going to be negative 1/12. Okay. Now, that is the distance we're going to go to the left and right. And it is to the left and right because this graph here would have been, whoops, this vertex at 2, negative 4. This negative 3 for an x equals y squared equation means the graph goes this way. So we're going to have to go, the focus is 1/12 this direction. That's focus. And the directrix would go an x equals equation right here, directrix. So for the focus and directrix, we're going to have to go 1/12 away from 2, right, the x value, in the left direction, and 1/12 away from 2 in the right direction. So 2 plus or minus 1/12, right? So I'll just look at 2 minus 1/12 to begin with. That is 24/12 minus 1/12, and that is 23/12. This is going to be the focus point. It's going to be at 23/12, comma, negative 4. And I'm not going to say the decimal equivalent to this. And you know what? I'm not going to say the improper fraction version either. It's, you know, it's 1 and 11/12, right? But it's going to be that right there. I don't know what the decimal is. It'll repeat forever. So that's something I don't really want to look into. That's why we don't always do decimals. The directrix, we're going to do 24/12 plus 1/12, which is 25/12. So the directrix is an x equals equation, and that is 25/12 like that. So like I said, those answers are brilliant, genius, perfect, exactly the way that I mostly want it to go. And those are the answers. That's what we're trying to get. As far as transformations go, we reflect. Now, this time we don't reflect over the x-axis, but we reflect over the y-axis because it is an x equals y squared equation. It's going to be going instead of that way, but that way. P is 12 times smaller, so A is going to be 12 times larger. You horizontally stretch by a factor of 12. Last time, hold on a second. I might have said, did I say this one correct then? I did. P was 1/4, so A became, yeah, stretch. Perfect. Okay, horizontally stretch by a factor of 12. And then we are also going to translate. We're going to translate 2 units right and 4 units down. Okay, one more, number 46. We got x equals 4 times y plus 5 quantity squared minus 1. So the vertex is at hk, negative 1, negative 5. Hopefully you're getting used to that. For an x equals y squared equation. The axis of symmetry is going to be at y equals negative 5. The p-value is 1 over 4a. So 1/16. And we're going to go 1/16. It's an x equals y squared equation, but this time this graph goes to the right. So this is at negative 1, negative 5 for your vertex, like that. Vertex, negative 1, negative 5. And we're going to go 1/16 to the right for the focus because this graph goes this way. So focus is over here, and directrix is over there. So from negative 1, we're going to add 1/16, right? So negative 1 plus 1/16 is, you might know that, but negative 16/16 plus 1/16, which is negative 15/16. So your focus is, that's the x value. The focus is negative 15/16, comma, and the height's the same of, what was it, negative 5? The directrix, we're going to go 1/16 the other direction, so negative 17/16. X equals negative 17/16. It's a vertical line, and it looks like that. Transformations, we do not reflect at all, but we do horizontally, let's see, P was 1, now it's 1/16. So A is going to be 16 times larger. So we are going to vertically stretch by a factor of 16. And we translate our vertex stuff, 1 unit left and 5 units down. Okay. Well, I think we have 8 more problems here. We go to 54, right? Modeling with mathematics. Scientists studying dolphin echolocation simulate the projection of a bottlenose dolphin's clicking sounds using computer models. I can't do it. I don't have echolocation. The models originate the sounds at the focus of a parabolic reflector. I'm glad they finally tell us what the focus is going to refer to this time. Models originate sounds at the focus. The problem in the graph shows the cross-section of the reflector with focal length of 1.3 inches. So I guess that's to F, to the P, your P value, and aperture width of 8 inches. So it's this drawing, and I'm going to copy and paste that drawing just to give those measurements here. I'm going to cheat a little bit. Write an equation to represent the cross-section of the reflector. What is the depth of the reflector? Okay, so number 47. Okay, so on number 47, I got this. Here we go. So on 47, we have a p-value here. This is p equals, and I guess it's 1.3. It's inches, but we'll get to that. Aperture, the entire thing there is 8. That's going to be used later. Write an equation to represent the cross-section of the reflector. It's all based on, A and stuff. The vertex is at the origin, so we're good there. It looks like an x equals y squared equation, but A is going to be 1 over 4p. So that's 1 over 5.2. Now, that's probably an accepted answer in some levels. I do not personally like decimals and fractions, so I'm not going to write it like that. If I multiply everything by 10, that becomes 10 over 52, and if I divide those by 2, you get 5 over 26. So I'm going to write it like that. This will be x equal, it's not a part A, but x equals 5 over 26 y squared. That's going to be my equation. Now, I may have to use a calculator for some stuff here. I'm not really sure. But what is the depth of the reflector? The reflector... So, wait, what do they say? The models originate sounds at the focus of the parabolic reflector. Oh, so the depth is just how far. So if the aperture is 8 inches here, we got to basically figure out what this length is right there. And to figure this out, we need to figure out a y value, what the y value is at, what the x value, I'm thinking of it rotated. We have to figure out what this x value is at a y value of 4 or negative 4. It doesn't really matter which one, but the x and y is negative 4. Why am I saying that? Because this distance is 8 across, parabolas are symmetrical, and this vertex is at the origin. So 8 is 4 up and 4 down. This x negative 4 and this x positive 4, it's the same x, we just got to substitute one of them. Doesn't matter, we're going to square it, it's going to turn positive. But what's that x value? And then that'll get you your distance of your depth. So, for depth, x equals 5 over 26 times, I'll just use 4 squared, which is 5 over 26 times 16. Now 16 over 26 can reduce as values there, and you get 8 over 13. So we get 5 times 8 over 13, which is 40 over 13 inches. This time I'm actually comfortable using a mixed, see, I don't want to use a decimal, but I am actually comfortable using a mixed number for a word problem, and that becomes 3 and 1/13 inches. That is the depth of that thing right there. That's the x value that we get. 40/13 inches is fine, but a mixed number works for context and those kinds of problems. And that's number 47. Okay, number 48, modeling with mathematics. Solar energy can be concentrated. Let's see. Solar energy can be concentrated using long troughs that have a parabolic cross-section as shown in the figure. Okay, I see the cross-section. I'm just trying to see what we do from there. Write an equation to represent the cross-section of the trough. What are the domain and range in the situation? What do they represent? Okay, so I'll probably have trouble on the very last part where they represent, because I don't know all these science things. I know that parabolas are used here, but I don't know the terminology with them. I'll have to look back at the problem. But what we do see is this cross-section here where that 1.7, that top thing is really going to be our focus. So when it comes to a cross-section based thing here, and we can have a vertex at the origin. They just said write an equation. So if we have this thing right here, your vertex is going there. This thing hits right there for some focus, and that focus is going to be 1.7. Excuse me, that's P. Your P value is going to be 1.7 based off of your vertex being there. So when they say write an equation, we're going to go ahead and say that A is 1 over 4P, like that, which is 1 over, I think that's 6.8. And I'm going to do the same thing as last time. I'm going to multiply that stuff by 10 and get 10 over 68. Divide both top and bottom by 2, and you get 5 over 34. And that's my best reduced fraction without a decimal in that answer. So my version of my equation is going to be y equals, and I'm going to make it a y equals equation this time. Y equals 5/34 x squared. So there's the equation. They do say, after that, what are the domain and range in this situation? Now, based on this graph here, we also notice that this width is 5.8 meters. So from here to here, we're getting 5.8, which means that this distance goes, half of 5.8 is 2.9. So this is 2.9 comma 0, things like that. And this is negative 2.9 comma 0. So your domain goes from negative 2.9 on x to positive 2.9. And that is in meters. The range, I need to find the range by substituting, because it's just for the trough itself, right? Is that what this thing's called? A long trough. The range, I have to substitute. It's not the 1.7. That's the focus on a part that's not the trough here. Or is that? Are they mentioning, is this 1.7? Okay, I think 1.7 is this guy. I believe it is. They better not be messing with me on that. Solar energy and parabolic trough, an equation represent the cross section of the trough. I'm hoping they're referring to this as the 1.7 right there and not necessarily the top of the corner. I don't think they are, so I think that's fine. The range, we have to figure out, it's from 0 on y all the way to the top of the trough, and we have to do that by substituting, say, 2.9 or negative 2.9 in for x to solve for y. So this y equals, and I'm going to try some stuff without a calculator, 2.9 is 29 tenths, and I'm going to go ahead and square that. I don't know 29 squared though, so this might be problematic. 29 squared is, I shouldn't spend too long on this. I think it's 841. So we get 5 over 34 times 841 over 100. 5 over 100 reduces to 1/20th. And 34 times 20 is 680. So you get 841 over 680. Now, I don't think I can reduce that. I assume this is, I mean, it's going to be a prime number because it's 29 times 29. So if anything, that's one. I don't know if they want me to round that. I'm sure there's a good rounding thing. Let me see what that is actually as a calculator. Let's see if 29 times 29 is 841. It is. So 841 over 680. It's 1.2367. It's not a great number overall. I'll just say 1. And I don't know if this is correct just because I can't see if that line's supposed to represent the depth. They don't really tell us, and it's not really a good measure there. I'm assuming that top is with the focus, but maybe it's not. So I apologize if that's not supposed to be just 1.7. Maybe it's 1.7. And then if it is, oops. So sorry about that. I'm really focused on that focus aspect of things. That's where I'm kind of But if that's the case, then that's not your equation, right? Your equation would have to be something else, and we'd have to find it out based on figuring out A. And I'm not really doing that. So I'm going to assume it's this, which is really weird. This is 1 and 161 over 680 meters, which is just weird. 1 and 161 over 680 meters. What do they represent? They represent the left-right distances. Let's see. These represent the left, right, and up, down distances of the trough from the vertex of its cross-section. Parabolic cross-section. So the problem with this graph, once again, is when they show that dotted line, and the reason I'm convinced that this thing is talking about that top part assuming that's the bit of the focus, is because this corner, although that shows the dotted line there, it doesn't show it on that. See, here's that corner there. I just don't know. It's just a little iffy. I don't know how many of these parabola things actually have a true focus. It says they're concentrated using long troughs, so I assume that's part of solar energy. I know I'm over speaking on it, but I want to be precise. I want to be correct, and I don't know if I am. I'm talking through it though, right? I don't know how many of you guys have this problem. Number 49, abstract reasoning. As the absolute value of p increases, how does the width of the graph of the equation y equals 1 over 4 px squared change? Explain your reasoning. Well, we've seen a bunch of graphs with this thing right here. As p gets larger, right, as we get this, like I can have a graph that looks like this, and your f and your p, or your f and your d are going to look like that. Whereas if your graph gets wider, suddenly this gets taller and this gets farther away. P is the distance from focus to vertex, focus to directrix. As p gets bigger, your graph gets wider. That's basically the thing. And you can tell in your equation, y equals 1 over 4 px squared. As p gets bigger, your a value gets smaller. If your a value gets smaller, it gets more vertically compressed. So let's go ahead and, how does the width of the graph of the equation change? So as the absolute value of p increases, the width of the graph also increases. This is because in the equation, p is in the denominator. And increasing p decreases a. I guess I gotta use a in italics, otherwise you're like, a what? It decreases a what? So let's italicize all these. It decreases a, which, let's see, which vertically compresses your graph, thereby increasing its width. I mean, it's an all real number domain, but the idea of it's getting wider. Okay, number 50. How do you see it? The graph shows the path of a volleyball served from an initial height of 6 feet as it travels over a net. So they don't even put the 6 on that, so I'm going to go ahead and do something like that. So we have the serve, 6 feet above ground right there. And it hits some arc, some point at B. I don't know what we're going to do with this yet. And it's working down that way. Parabolic arc. There's some A, there's some C. We're going to refer to that in a bit. Okay. Label the vertex, focus, and a point on the directrix. So I guess that's what they're talking about here. The graph shows the path of a volleyball serve from an initial height of 6 feet as it travels over a net. Oh, label them. Okay, so this is the focus, and this is, I don't think they want actual numbers. This is the point on directrix, and this is the vertex. Okay, an underhand serve follows the same parabolic path, but is hit from a height of 3 feet. How does this affect the focus and the directrix? So it follows the same path, so what's going to happen is everything's going to shift downward. Okay, so because it follows the same path, it has the same A. Because it has the same A, it has the same P. And everything goes from 6 feet here now to 3 feet, like that. But everything just goes down with it, right? Just goes like that instead. So, and I know I didn't really do very much stuff on that, but just that's the idea. So I'm going to undo all that and go back. They don't ask us to explain, but everything shifts down 3 units because that distance there. So the vertex, focus, and point on directrix are all 3 units lower than they were before. And really the reason is because, once again, if it's the same parabolic path, A didn't change. Because A didn't change, P didn't change. Because P didn't change, your distance from vertex to focus didn't change. Neither did vertex to point and directrix. It just went 3 units down lower. How does it affect them? Everything is 3 units lower than before. Kind of a weird question. I don't even know what focus and directrix will have to do with those kinds of things because it's not engineering, but of course every parabola has a focus and directrix, so that's fine. The distance, I mean, I know what they have to do with it. I just don't know if there's a scientific reasoning on why I need the focus and directrix of that parabolic path. The distance from point P to the directrix is 2 units. Write an equation of the parabola. Okay, let's copy what that thing shows so I can use it. Okay, so the directrix, what did they say? The distance from P to the directrix is 2 units. Okay, so what we need to understand is that the directrix will be underneath here. Let's do actually a different color. Let's use this like red. So the directrix is going to be down here. Okay, it's going to be that horizontal line. Now, 2 units down from here, it's 2 units away from this point, right? So this is 2. That's not P, but this is 2. So the directrix is going to be the equation y equals -1. That's what's important. This can help us find P. So if the directrix is y equals -1, the vertex is at 0, 0. This is 1 unit away, which means your focus is also 1 unit away. So that's at 0, 1. P equals 1. When they say write an equation of the parabola, that's all I really need to get. I don't care about the -2, 1 in particular, other than 2 units away is at y equals -1, da, da, da. And now I can get my A value. A is 1 over 4P, which is 1/4. Your equation is y equals x squared with your vertex at the origin. The equation is y equals 1/4 x squared. And to confirm that, I can substitute -2 into here. -2 squared is 4, and 1/4 of 4 is indeed 1. So we do hit that point. That's number 51. Number 52, 3 more problems. Thought-provoking. 2 parabolas have the same focus, AB, and focal length of 2 units. So the focal length is P. Write an equation of each parabola. Identify the directrix of each parabola. 2 parabolas. So when they say 2 parabolas, I guess that they're saying like 2 different parabolas, if that makes sense. So they're not the same ones. Have the same focus at AB and focal length of 2 units. Write an equation of each parabola. Identify the directrix of each parabola. So when they're saying focal length of 2 units, I assume they mean P is a positive value for that. So we can do something like this, right? We can do, I'm kind of going along with this, A comma B. So here's A, say, and here's B. So here's your focus for 2 different graphs, A, B. Now the focus is inside your parabola. So I could have, say, a parabola that goes this way, and maybe a parabola that goes this way. And in both of them, oh, that's not even close to the same distance. And a parabola that goes, say, this way. And both of them will have this p-value is 2. This p-value is 2. The reason why I did them this way, rightward and upward, is because that can keep my p-value positive in both of these. Now, they have 2 different vertexes. This vertex to this guy, I know the drawing's really strange, but the vertex to this guy is 2 less from this A. That's A minus 2, comma B. Vertex from this guy is 2 less than B. That is A, comma B minus 2. They say write an equation of each parabola, identify the directrix of each parabola. So as far as equations go, let's do these in different colors. This one I'm doing purple. The other one I'm doing green. So for the first one, it's an x equals y squared equation. The p is 2, and if the p is 2, then the a value is going to be 1 over 4 times 2, which is 1/8. A is 1/8 for both of these. So this first equation, being x equals y squared equation, is x equals 1/8 times, and you have y minus b, quantity squared, plus, and then a minus 2 is going to be the h of your vertex. So it's going to look like that. It looks strange, but that is the equation of this one that I can use. This one in purple, a comma b minus 2, this is a y equals x squared equation. So it's y equals 1/8, different purple, 1/8 times x minus a, quantity squared, plus k, b minus 2, like that. Those are the 2 equations. Now they're saying write the equation. Give me 1 second. Just a runny nose, I have to take care of it. Okay. Now they're saying identify the directrix of each parabola. If the focal length is 2 units here, another 2 units down gives us our directrix. So it's another 2 units down from here. So this one's directrix is going to be y equals b minus 4, another 2 units down from that y value. And then this one's another 2 units left from whatever this x value was. So this is going to be a directrix of x equals a minus 4. Very interesting problem when all is said and done. But that's, I believe that's what those things are going to be right there when it comes to equations and yada yada, all that jazz. Okay, that's 52. 2 more. Number 53, repeated reasoning. Use the, I thought we were off this. Use the distance formula to derive the equation of a parabola that opens to the right with vertex 0, 0, focus P0, and directrix x equals negative P. Let's go ahead and copy and paste that visual in here, and let's figure out that whole 1 over 4p nonsense for x equals y squared. I think they did it for y equals x squared, and so they're saying do it for x equals y squared. Okay, so number 53. I mean, it's good to do it. I'm not actually upset. So the distance here, FP, is going to be equal to this distance, PD. We're back to that. Now the distance from F to P, we have x minus P quantity squared, square root of x minus P quantity squared, plus y minus 0 quantity squared, that's y squared, and that equals PD's length. The distance from x to negative P is x minus negative P, or x plus P, like that. I'm going to square both sides. So I'm doing distance formula. I'm just, skirting past some parts. Square both sides here. I'm going to expand x minus P quantity squared. That'll be x squared minus 2 times xp, or px, let's see, px minus 2px plus p squared, and there's plus y squared. X plus p quantity squared will be x squared plus 2px plus p squared. Subtract p squareds, they cancel out. Subtract x squareds, they cancel out. And you're left with negative 2px plus y squared equals 2px. I'm going to add 2px to both sides. Okay, so we get y squared equals 4px. And we divide both sides by 4p to solve for x. So divided by 4p, like that. So x is going to equal, I'm going to put the 1 over 4p in front, 1 over 4p y squared. And that's the equation they're kind of going for, right? I always say a y squared, a is 1 over 4p, that kind of thing. But that is the, that's the bit. That's the bit. And the last question, we have number 54 on problem solving. The lattice rectum of a parabola is the line segment that is parallel to the directrix. I didn't even know this. I didn't know its name, so this is new for me. Passes through the focus and its endpoints that lie in the parabola. Find the length of the lattice rectum of the parabola shown. Okay, so let's copy and paste that. I'm done drawing things if I don't need to, if they have something for me. Okay. Find the what? The length? Okay, so here's what I'm going to do. I see this as a y equals x squared equation. We have to find the a value. The p is obviously 2 for this one, right? P is 2 from 0, 0 to 0, 2. So your a value is going to be 1 over 4 times p, or 1/8. So your equation to this thing is y equals 1/8 x squared. Now, as far as the length goes, notice that because it's parallel to the, what'd they say? Parallel to the directrix. It's a horizontal line, which means the a and b will be the same height, means they have heights of 2. This is some x comma 2 and negative x comma 2, that kind of thing. The y value is 2. I have to substitute 2 in this equation for y, and I'm going to solve for my x values. Those x values I need to find their distance of. If I multiply both sides by 8, I'll get 16 equals x squared. And if I take the square root of both sides, I'm going to get x equals positive or negative 4. There's more than one answer. That means the a value is at the point negative 4, comma 2, and the b value is at the point positive 4, comma 2. That's how that thing's working out. So the distance from negative 4 to 4, that distance is the absolute value of negative 4 minus 4, which is absolute value of negative 8, which is 8. 8 units. That is the length of the lattice rectum of this parabola shown. Okay, guys, and that ought to do it for this one. So outside of perhaps that one problem, one or two problems where they have a word problem, and I don't really know if they're asking for the focus or something else, especially that trough question. I apologize if I was looking at 1.7 as the focal length and not the depth. I have no idea, and you probably don't have that problem. But outside of that, this seemed to be okay. I know a lot of this stuff hits a little harder in IM3, and you're probably not looking at this stuff again in IM2 because this is the only time we feature parabolas here. It's nice new stuff to talk about. You get to practice some of the graphing with stretch factors and compression factors, even though they're very extreme. And I'm sure we're going to hit some of these questions again on review and the chapter test. Now, I don't know when my next video will be out. I'm kind of busy when I'm working on these things here. Maybe within the next week, we can try and hit those. But I still have one more section on just different graph types, I think, the quadratics, linears, and exponentials, and we'll see when I get that one up. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.